divided by pi raised to the 0.5 power is that the radius is 1.069 times 10 to the minus fourth meters. And so if I multiply that by 2, that's the radius, right? So if I multiply that by 2, it's 2.138 times 10 to the minus fourth meters is the diameter, sorry. Right? And then it's like, how many millimeters is that? Well, it's actually 0.21 times 10 to the minus third meters. And 10 to the minus third meters is a millimeter, and you guys can't see that because it's like behind stuff. It's like, got to move the stuff. There's stuff. Move the stuff. Right? So ultimately I get 0.21 times 10 to the third. You could just leave it like this. This is entirely fine if you don't want to do the millimeter dance. One last thing before we go on and look at something else. Okay? Notice that it's giving these at 20 degrees Celsius. Why? Yes?
Because heat would make it more? Or less?
Heat would make it more. Yeah, for wires, that's true. For wires, it's true that heat makes the resistance more, and that's because, why? Because if you imagine those electrons kind of making their way down the freshman hall or something like that, right? The motion of the freshmen affects the speed with which travel can go down that hall, correct? And hot wires, the freshmen are moving fast, yes? And it's hard to get down the hall, and when they're cold, they're moving slowly, right? And it's easier to move down the hall. This is why, one of the reasons why superconductors superconduct at low temperatures, at very, very low temperatures. Okay? It's not the entire picture, there's actually a quantum thing, but basically thermal effects mess with current. Okay? Now, that's true for wires. For diodes and semiconductors, it's actually the opposite. When you heat them up, they conduct more. And this is why stereos burn out, right? Because you turn up the volume, the resistance decreases as it gets hotter, and then more current flows, so it gets hotter, so more current flows, so it gets hotter. It's called thermal runaway or something like that, right? But for wires, it actually causes an equilibrium. The wire will heat up until it limits the current, and then it reaches an equilibrium, right? So that light bulb heated up until it actually started decreasing the current, right? Example 1, let's try. Okay, so a copper wire is 1,610 meters long. That's a mile. It has a cross-sectional area of 4.5 times 10 to the minus 6 square meters. That means that it has a 2.4 millimeter diameter, right? Which means that it is basically half a centimeter, isn't it? In diameter. Wait, I'm sorry, diameter. No, it's a quarter of a centimeter in diameter. So it is a radius about as big as, well, this wire here. Let's make this wire a mile long. What is its resistance? Just use this. You're going to use this formula here. If we made this wire a mile long, got to creep out the kids that watch this video that aren't from this school. I did. Oh, no dear. Yesterday I had a birthday and there were like a bunch of freshmen sitting there, and I'm marching around the room and yeah, I'm marching around the room and and the kids are just like staring at me like I'm a space alien, which I think is totally unfair, right? So I gave them a stern look because all the kids were laughing at me in this class, but I don't think they could necessarily hear that. That's right. So I gave them this look. They still laughed a little bit, some of them. I should have done the mustache with it. The mustache would be. Yeah, that's right.
That is impressive, Mary.
Yeah. Oh, I just wanted you to know. I wanted the first problem to be easy. Yeah. But it's like, what on earth is 4.5 times 10 to the minus 6 square meters? Right?
Now you know.
That is this cross-sectional area of this wire here. Yeah? Does that help? Put it in like some sort of perspective? The next problem I'm going to give you, you have to figure out like the radius or something like that. But okay, I better stop.